National requirements often drive extreme aircraft characteristics. The U-2 overflew Moscow and was seen on radar, and pictures showed surface-to-air missiles being deployed. President Eisenhower directed that a new aircraft be created, not flying at 450 miles an hour, but 2,150. Not at 70,000 feet, but at 85,000 feet, and would be America's first stealthy airplane. When you're flying an airplane at Mach 3, the surface temperature will exceed 600 degrees. The airplane will grow 3 to 4 inches in length, an inch or two in width. Aluminum can't be used, so 93% of the aircraft is made of titanium. Special fuels had to be created, JP7, to withstand the high temperatures. Normal fuel has a flash point of minus 40 degrees. JP7 is a plus 335. Electric ignition would not work, so the chemical triethylene borane, which explodes at 3,000 degrees, is used to start the engine and to light the afterburners. Stealthy airplanes, by their nature, are unstable. So on the pedostatic in the front of the airplane, there's a side probe. It has a hole on the top and the bottom on either side. It's measuring the airflow to see if there's divergence in the yaw and the pitch, and it is putting in slow inputs to keep the aircraft under control. When you're traveling at 35 miles a minute, navigation is a real challenge. This is the first airplane that had an automated star tracker. We guaranteed the president 300 feet anywhere in the world traveling at 2,200 miles an hour. The real genius of the airplane is the integration of the inlet, the engine, the bypass tubes, and the afterburner. This combination would allow you to cruise at 3.2 Mach. And the best way to depict it is to start you on the ground and take you through a climb profile. You've started the engines, you've taxied, you're on the runway, you release the brakes, you light the afterburners. In 20 seconds, you will have gone over 4,500 feet. You're lifting off doing 210 miles an hour, and you're going to cross through 20,000 feet in less than 2 minutes from the time you release the brakes. To get through the high drag area with this airplane, we would climb to about 33,000 feet at 0.9 Mach, lower the nose, go to maximum burner, and accelerate through 1.1 Mach, the high drag regime, and then start the climb again. Around 1.7 Mach, the spikes would unlock and we'd make sure that they were moving aft. The spikes were absolutely critical to keeping the shock wave inside the inlet and to allow for the compression, which sets up the ram effect. At 1.8 to Mach 2, the inlet guide vanes, which up until this point had been straight ahead to let all the air in, would turn to a camber. The excess air would now be picked up by the aft bypass tubes, which goes around the engine, which is 2,000 degrees, directly into the afterburner, which is 3,400 degrees, which needs additional air for cooling, and you also get additional thrust. This is the only airplane that I'm aware of in the world. The faster we went, the less fuel we burned. Our normal cruise speeds were Mach 2.8, 3.0, 3.15, or 3.2. On your first mission in this airplane was subsonic. We took you up to a tanker to learn to refuel and then practice landings. Tankers were absolutely vital to us because every 2 hours we had to come down from altitude and either refuel or land after we had traveled over 3,000 miles. This absolutely remarkable airplane is still ahead of its time. The absolute speed record still stands of 2,193 miles an hour, set in 1976.
Beginning with the Wright brothers' initial flight in 1903, there's been a continual push to ever faster speeds. The Wright's first flight was estimated an airspeed of about 31 miles per hour into a headwind of 21 miles per hour for a ground speed of only 10 miles per hour. The first recognized speed record was Alberto Santos Dumont in 1906, clocking in at a ground speed of just over 25 miles per hour. Just 6 years later, the fastest plane was already 4 times faster, as the 100 mile per hour barrier was broken in early 1912. By 1920, the world's fastest airplane was the Newport Delage NID-29V biplane, with an officially recorded top speed of 194 miles per hour. By the end of the 1930s, at the dawn of World War II, the official record was 466.6 miles per hour, held by the German Heinkel HE-100. Following the war, things really started to accelerate with the advent of jet engines. In late 1945, Hugh Wilson piloted the turbojet-powered Gloster Meteor F Mark IV to a speed of 606 miles per hour. In the mid-1950s, the fastest official speed record jumped up to 822 miles per hour in the North American F-100C Super Sabre. In 1958, the record jumped again, up to 1,404 miles per hour, set by the Lockheed YF-104A Starfighter. And by 1976, the Lockheed SR-71 Blackbird flew at 2,193 miles per hour, a record that has remained unbroken. In this lecture, we'll learn about the science that makes such achievements possible. How fast can a plane go? How high can a plane go? This is the realm of extreme flight. But these are questions that have surprisingly precise answers, which aircraft designers and pilots must know and understand. Drastic and catastrophic failure can occur if a pilot or designer pushes too far beyond the performance limits of an aircraft. The flight envelope, also called the performance envelope, is the traditional expression for a set of performance limits, primarily defined by 3 characteristics. 1, the maximum power available from the propulsion system. 2, aerodynamic drag and the power required to overcome it. And 3, aerodynamic stall. First, let's talk about the power available from the propulsion system. It's important to recognize that there is a key difference between a jet aircraft and a propeller aircraft when it comes to performance limits. The fundamental performance limits of these propulsion devices are different. Jet aircraft are thrust limited, while propeller aircraft are power limited. This difference has an impact on how the performance characteristics are determined and what the optimum flight conditions end up being. Now, what exactly is the difference between thrust and power? Well, thrust is just a force, while power is the work done in a given amount of time, or the rate of energy change. Since work results from applying a force through a distance, we can think of power as force times distance in a given time. Jet engines have a fundamental limit based on thrust, because the engine burns fuel to directly create pressure differences that produce the thrust. So the performance of jet engines is rated in pounds or newtons. By contrast, propeller aircraft driven by internal combustion engines are power limited, because the energy released from the fuel is used to apply a torque to a shaft that rotates a propeller, and time-normalized torque is power. So the performance of internal combustion engines is rated in horsepower or kilowatts. For an aircraft in flight, the power required for flight can be found by multiplying the thrust times the speed of the aircraft. This is dimensionally consistent, since a force times a distance per unit time is energy per unit time, which is power. Now, for our discussion here, we'll focus on aircraft driven by a propeller mounted to an internal combustion engine, which is power limited. Jet aircraft have very similar limitations, but the key limiting factor for a jet's max speed is thrust instead of power. We saw in Lecture 7 that the shaft power supplied by the engine is transmitted to the flow by a propeller, and the power available from the engine-propeller combination can vary across a range of airspeeds, since the propeller efficiency varies with airspeed. If the aircraft has a constant speed propeller, which automatically adjusts the propeller pitch angle to optimize efficiency at a given operating point, then the power produced by the engine will be relatively constant across a range of airspeeds. In any case, it's only maximum power that defines the edge of the flight envelope. So let's turn our attention to the power required to move the aircraft through the air. This power required will set the maximum speed for an aircraft in level flight, and can also set the minimum speed in some cases. How can we find the power required for flight? Well, if an aircraft is in steady level flight, we know that the forces acting on the aircraft must be in equilibrium. So the thrust must equal the drag. The thrust required for steady level flight is directly equal to drag. But thrust is not the same as power. As we just saw, power is a force acting through a distance per unit time. So we can get from thrust to power by simply multiplying by velocity. Or in other words, the power required for steady level flight is just drag times airspeed. So let's revisit aerodynamic drag and consider how it impacts the performance of an aircraft. There are two main types of aerodynamic drag: parasitic drag and induced drag. And aircraft designers have a very nice, succinct way of representing the parasitic and induced drag characteristics of the airplane in what is termed the drag polar. This is a plot of the drag coefficient as a function of the lift coefficient. When lift is 0, induced drag is 0, so total drag is solely parasitic drag. Then, as the lift increases, induced drag goes up and the overall drag goes up. The amount by which the induced drag goes up, or the amount of curvature of the plot, depends on the values of the aspect ratio of the wing and the Oswald efficiency factor for the aircraft's dragginess. So overall, drag is the sum of parasitic drag coefficient and the induced drag coefficient. And the induced drag coefficient is equal to the square of lift coefficient divided by the product of pi, the aspect ratio, and the Oswald efficiency factor. This is the equation for the drag polar, which directly affects the aircraft's lift-to-drag ratio. And lift-to-drag ratio is a measure of the aerodynamic efficiency factors into so many performance metrics. The parasitic drag coefficient, or zero lift drag coefficient, is approximately constant, since it describes how aerodynamically clean the aircraft is. It's a combination of the pressure drag and the viscous drag, which are relatively constant when expressed in coefficient form. Taking a look at the drag equation written for parasitic drag, with a fixed parasitic drag coefficient, the aerodynamic drag goes up quadratically with airspeed. For every doubling of airspeed, the amount of parasitic drag quadruples. When we plot parasitic drag versus airspeed, we readily see the dramatic rise in drag as the airspeed goes up. The induced drag, however, is a very different story. The magnitude of the induced drag is directly related to how hard the wing is working to produce lift, which is described by the magnitude of the lift coefficient. Let's bring back the lift equation, which said that the required lift coefficient for a level flight condition depends on the flight velocity. The more slowly the aircraft flies, the harder the wings have to work in order to sustain lift, and the higher the lift coefficient will be. And with a higher lift coefficient, there is higher downwash, stronger wingtip vortices, and increased induced drag, since there is wasted energy in the tip vortices. We saw in Lecture 5 that the induced drag coefficient is proportional to the square of the lift coefficient and inversely proportional to the aspect ratio of the wing and the Oswald efficiency factor. And from the lift equation, the required lift coefficient for a level flight condition depends on the flight velocity. The more slowly that an aircraft flies, the higher the lift coefficient must be to sustain flight, and the higher the induced drag coefficient becomes. When we combine all of these effects into a single relationship, we see that induced drag is inversely proportional to the square of the flight speed. So if an aircraft reduces its speed by a factor of 2, the induced drag will go up by a factor of 4. We've seen that parasitic drag goes up with the square of flight speed, yet induced drag goes down with the square of flight speed. When we plot both of these drag trends together, along with the trend of overall drag, we see several intriguing things. First, low-speed flight is dominated by induced drag. Second, high-speed flight is dominated by parasitic drag. And third, in between these two extremes, there is a condition for minimum drag. Now let's map this insight onto the power required for flight across a range of airspeeds. Since power required is simply drag times velocity, We can take our data for induced drag, parasitic drag, and total drag and multiply each by the range of airspeeds involved. This gives us curves for parasitic power required and induced power required, which add up to give the total power required. Now here is how the power required and power available work together to define the performance limits of an aircraft. Let's overlay the maximum power available and the power required curves. If we wish to sustain equilibrium flight, we see that the maximum power required cannot exceed the power available. So the intersection of these curves constrains the operating envelope. The aircraft can fly at any of the speeds between the minimum or maximum speeds, and there is an optimum speed corresponding to the minimum power required. Let's discuss the implications of each of these three features: low speed limit, max speed, and minimum drag, which define the operating envelope. For low speed flight, it's a bit non-intuitive to recognize that aircraft drag, and thus power required, actually increases as flight speed decreases when flying at low speeds. This trend is what Samuel Langley, the secretary of the Smithsonian Institution, had confirmed during his failed attempts at flight during the same period as the Wright brothers. Langley actually did some experiments using a whirling arm to determine the lift and drag properties of a wing in flight. He had carefully and correctly measured a trend of decreasing drag with increasing speed, where drag due to lift is dominant. His error was in extrapolating this slow speed trend to higher flight speeds, where parasitic drag becomes dominant. Langley didn't recognize that there were different components of drag that he had to separate out. Pilots can also encounter difficulty when flying at low enough speeds where lift-induced drag is dominant. A pilot's intuitive approach to flight is that a power reduction corresponds with slower flight. This seems obvious, since it's what everyone does when driving a car. However, if a pilot is at low speed flight and wishes to decelerate while maintaining level flight, the power must actually be increased. This is because the induced drag goes up at the lower flight speed, and extra thrust must be produced in order to match the increased drag and sustain flight. This non-intuitive relationship is so vexing that pilots have given it a name. It's called flying on the backside of the power curve. Flying on the backside of the power curve can also lead to some serious accidents if a pilot isn't careful. For example, a pilot may pull back on the throttle in slow flight in an attempt to slow up just a bit more. However, since more power is actually required to maintain level flight at a low airspeed, the aircraft will start to descend. A poorly trained pilot will try to counteract this descent by pulling back on the stick, which increases the angle of attack, increases the drag, and causes the aircraft to descend at an even higher rate. If a pilot isn't careful, this could become a vicious cycle, leading to the aircraft to mush along at low speed, but descending at faster and faster rates all the way to the ground. Instead, the correct approach to this scenario is to add power, even though that's not the intuitive thing to do. So we've established that induced drag dominates the flight envelope at low flight speeds. In some cases, if stall has not yet occurred, induced drag can even impose a minimum speed on the flight envelope. But this is unusual. More often, aerodynamic stall on the wing is what sets the minimum flight speed of an aircraft, since stall often occurs at a higher airspeed before low speed power limit is reached. Aerodynamic stall occurs when the wing is working so hard that the flow ceases to follow the curvature of the wing. The flow separates from the wing, leading to a dramatic loss of lift. Aerodynamic stall is directly related to the maximum lift coefficient, which is characteristic and a constant value for a specific wing geometry. We see from the lift equation that if lift is held equal to weight and flight is at a fixed altitude or density, then there will be a minimum speed directly corresponding to a maximum lift coefficient. This is the stall speed. So even though power required may limit the minimum speed in some cases, most often the aircraft will stall first. If an aircraft must be designed to operate in the low-speed portion of the flight envelope, what tools might the aircraft designer use to optimize flight? Well, if we look at the expression for induced drag due to lift, we see that the weight of the aircraft and the wingspan are critical features. Induced drag has the square of aircraft weight in the numerator. So if the weight of the flight vehicle can be reduced, then there is a substantial reduction in induced drag, because the wing has to produce much less lift to support that weight. Also, we see that the square of the wingspan is in the denominator. If the designer can increase the wingspan, then the induced drag will also dramatically decrease, because the distribution of lift across the span has changed, such that the strength of the tip vortices is reduced. This is the exact strategy employed on the U-2 spy plane, which had long, thin wings of 103 feet for long-endurance spy missions during the Cold War. Now let's come back to our map of power required and power available to consider the high-speed flight condition. We recognize that high-speed flight is dominated by parasitic drag, which is a measure of how aerodynamically clean the aircraft is. Parasitic drag scales quadratically with flight speed until the thrust limit is reached. And since the power required is equal to the drag times the airspeed, the parasitic power required scales cubically with the flight speed. Much of the evolution of aircraft in the first decades of flight was driven by reducing the parasitic drag and increasing the power available, such that the aircraft could fly faster. For example, there came a point where aircraft designers were able to support the loads on the wing through internal bracing, rather than requiring external bracing wires. These struts and wires, while they are small, still produce very high drag. Elimination of the struts and wires enabled huge reductions in the parasitic drag coefficient and enabled much higher flight speeds. The Hughes H-1 Racer was meticulously designed by Howard Hughes with the specific goal of breaking speed records. Hughes custom designed and built the aircraft in the mid-1930s, incorporating innovative features such as hydraulically actuated retractable landing gear, including the tailwheel. He also relied upon flush rivets and countersunk flathead screws. The result was an incredibly smooth surface with as little disturbance to the airflow as possible. Even the fit of the landing gear in the retracted position was perfect, with no gap to be found. This resulted in a highly polished, sleek, and streamlined fuselage with an incredibly low parasitic drag. Indeed, the airframe is beautiful. For the power plant, Hughes selected the Pratt & Whitney R1535 engine, which is a twin-row, 14-cylinder radial engine. It had 1,535 cubic inches of displacement and was originally rated for 700 horsepower. However, Hughes and his team tweaked and tuned the engine performance to achieve 1,000 horsepower. Such a large air-cooled engine had to be expertly integrated into the aircraft, leading to the custom design of a cowling that optimized cooling airflow, yet minimizing aerodynamic drag. On September 13, 1935, just 1 month after the first flight of the Racer, Hughes broke the world speed record for a land-based aircraft, hitting an average speed of 352 miles per hour over a closed course near Santa Ana, California. In fact, he pushed the Racer so hard that he exhausted his fuel supply on board and ended up crashing. Thankfully, the crash wasn't too severe. He was able to walk away from the incident and ended up repairing the damage. Then, he refitted the Racer with a larger wing to lower the wing loading, which improved long-distance cruise efficiency, and flew it coast to coast on January 19, 1937, to break his own transcontinental speed record by nearly 2 hours, with a time of 7 hours, 28 minutes, and 25 seconds, with an average speed of 332 miles per hour for the entire trip. Underscoring the immensity of his feat, his Racer was the last privately built aircraft to break a world speed record, with military aircraft dominating the record books thereafter. Note that the world seaplane record at this time was 440 miles per hour, over 100 miles per hour faster than the land-based record. There's a fundamental reason why, and this again has to do with the wing. The reason that a seaplane could cruise so much faster than a land plane was that the wing of a seaplane could be more fully optimized to focus on maximum flight speed. A land plane typically has a runway of only 2 to 3 miles to get off the ground, but a seaplane can take advantage of the virtually unlimited runway available on water to rise into the air far more gradually. Thus, for a seaplane, takeoff can be so gradual as to be almost indistinguishable from cruising. This means that a seaplane wing optimized for cruising can, just barely, also be used for takeoff. Let's now turn our attention to the really interesting condition of minimum drag. This point is where parasitic drag is exactly equal to the induced drag. This condition of minimum drag represents optimum efficiency, with constant lift being equal to the aircraft weight and minimum drag, we have maximized the lift-to-drag ratio. And remember, the maximum lift-to-drag ratio is the condition for best glide performance, since the glide path angle is directly related to the lift-to-drag ratio. It's really important to recognize that the lift-to-drag ratio varies with airspeed, within which there is a specific speed associated with the minimum drag condition, which is L/D max. Also, the maximum value of lift-to-drag ratio is fixed for an airplane, but the speed at which it occurs will change depending on the weight. But the airspeed for minimum drag is not the same as the point for minimum power. Since power is equal to the drag times airspeed, the minimum power airspeed is actually a bit lower than the speed for minimum drag. This difference in the two optimums has some interesting consequences for propeller-driven aircraft. The speed for minimum power will give the best endurance, or time aloft, for the aircraft, while the speed for minimum drag will give the best range. Okay, so the power required curve dictates three key aspects of the flight envelope: low-speed flight characteristics, the maximum speed, and the optimum speed for efficient flight. Now, so far we've ignored the effects of air density, which we know will decrease as we go up in altitude. This variation in density has a profound impact on aircraft performance. Let's take a closer look at the implications of air density. Since the stall condition for a wing is governed by the lift equation with a maximum lift coefficient, we can explore the impact of density changes on the true airspeed for stall. Solving the lift equation for airspeed, we see that density appears in the denominator of the square root. Thus, lower density will increase the true airspeed for stall. For the engine, as the density decreases at higher altitudes, there is less air mass available for combustion, so the maximum thrust or power available from an engine decreases. Also, changes in altitude will have an effect on the power required, since density appears in the equations for power needed to overcome induced drag and parasitic drag. Power needed to overcome lift-induced drag is inversely proportional to density, so this so-called induced power goes up as the aircraft climbs in altitude. At higher altitudes, the wing has less air mass to work with to produce lift, so the lift coefficient must increase for a particular altitude. The wing must work harder, and the induced drag goes up. On the other hand, the power required to overcome parasitic drag will decrease at higher altitude, since there are fewer air molecules interacting with the aircraft and resisting its motion. Now let's combine these changes in induced power, parasitic power, stall, and power available to see how the operating envelope changes. As the aircraft gains altitude, the operating envelope shrinks. The minimum speed, dictated by either the stall condition or the power limited condition, will increase at higher altitudes. And the maximum speed, dictated by the maximum power available, will decrease as the altitude goes up. So the minimum and maximum speeds start to converge. This narrowing of the range of flight speeds at high altitude represents a very hazardous corner of the flight envelope. At the extreme highest altitudes that a given aircraft can fly, there is very little difference in airspeed between a full throttle condition and aerodynamic stall. This limit is true whether the aircraft is a power-limited propeller aircraft or a thrust-limited jet aircraft. High-altitude flight can be very dicey. It's so precarious that pilots refer to this as the coffin corner. A good example of the hazards of the coffin corner is the crash of Pinnacle Airlines Flight 3701. Two relatively young and inexperienced pilots were flying an empty CRJ-200 regional jet on a ferry flight. With a relatively light airplane, they decided to put the airplane through its paces. After doing an aggressive nose-up maneuver to pull 2.3 Gs, they decided to join the 410 Club by taking the aircraft to flight level 410, or 41,000 feet. This represents the highest operational altitude for this jet and the extreme edge of its flight envelope. They set the autopilot in a fixed vertical speed climb, bringing the plane very rapidly up to that altitude. As the autopilot attempted to maintain the commanded vertical speed, it dutifully pitched the nose up to greater and greater angle of attack. Simultaneously, as the aircraft climbed, the inherent stall speed crept up on them. Finally, after reaching 41,000 feet and struggling to maintain that flight condition, the aircraft entered a stall. The stall itself isn't so bad, but both engines flamed out. Before the pilots could get the engines restarted, the rotating components of both engines locked up due to different rates of cooling for different components in the engine. After about a quarter hour of failed restart attempts, the pilots finally acknowledged that they were in serious trouble. But it was too late. At this point, they had very few landing sites available to them, and they crashed several miles short of an airport, killing both of them in the process. Clearly, these young, inexperienced, and frankly unprofessional pilots were not prepared for the hazards that they encountered at the very edge of the aircraft's flight envelope. Let's now look at the effects of altitude on fastest rate of climb versus fastest cruising speed. At a particular altitude, the difference between the power available and the power required is termed the excess power. This excess power represents the capacity for the aircraft to increase its overall energy beyond its current equilibrium condition. This increase in aircraft energy could be a climb to higher altitude with higher potential energy. It could be an acceleration to a higher flight speed with higher kinetic energy, or some combination of the two. The maximum rate of climb possible for the aircraft directly depends on the magnitude of the excess power. Or the best acceleration performance will occur when there is maximum excess power. Examining a plot of the curves for power available and power required, the excess power can be represented as a vertical line extending between the two curves at a particular airspeed. The length of this line, then, is the magnitude of the excess power. If we plot the value of excess power across a range of airspeeds, we see that there is a clear optimum at a specific airspeed. If our goal is to climb to a higher altitude as quickly as possible, the pilot should put in full throttle for maximum power and pitch the aircraft to fly at the speed for maximizing excess power. Now, as the aircraft climbs, recall that the power available and the power required curves start to close in on one another. So the amount of excess power is going to diminish as the aircraft climbs, which will result in a gradually reducing maximum rate of climb. At a certain point, the rate of climb gets so low that, for all practical purposes, the aircraft can't climb any higher. A common definition of this condition is the service ceiling, defined as the altitude at which the aircraft's best rate of climb performance is only 100 feet per minute. That's barely 1 mile per hour. Under ideal conditions, with expert piloting technique, an aircraft could climb higher to its absolute ceiling, where the rate of climb goes to 0. But this condition is also at risk of the high-altitude stall behind the regional jet crash that we just discussed. There's also another bit of nuance whenever optimal performance is desired. Since the shapes of the drag curves are changing with altitude, the optimum airspeed for maximum excess power and best climb performance is changing. Thus, the speed for best rate of climb will be changing a little bit as the aircraft climbs, and the pilot should maintain the aircraft pitch for the best climb speed if optimum performance is desired. A key outcome of the climb speed of the aircraft is the time required to climb up to a cruise altitude. This is a highly desirable design feature for high-performance aircraft. The faster that the aircraft can climb to cruise altitude, the quicker it can reach efficient cruise conditions, accelerate to high speed, and get to its destination more rapidly. If the speed for best climb is flown continuously up to cruise altitude, the aircraft will have a minimum time to climb. For example, a lightly loaded Boeing 757 climbing from sea level could hit a peak rate of climb close to 5,000 feet per minute, which would bring it to cruise altitude of 38,000 feet in just about 15 minutes or so. That's a pretty aggressive climb. Now, we've been talking about optimizing climb performance based on minimizing the time to climb. However, we can also optimize by minimizing the horizontal distance needed to perform a climb. For an aircraft taking off from a short runway with an obstruction at the end of the runway, the critical thing that the pilot worries about is clearing that obstacle rather than minimizing the time to climb. Thus, the pilot cares about gaining as much vertical altitude as possible within as little ground distance as possible. This equates to the maximum climb angle, which is a different condition than the maximum rate of climb. We can find the maximum climb angle with a graph that's sometimes called a climb performance hodograph. The best rate of climb condition is found as before, with a maximum rate of climb clearly indicating the flight condition for optimal vertical speed. The condition for best angle of climb is found by recognizing that the climb angle is proportional to the vertical speed divided by the horizontal speed. So the slope of the line connecting the origin of this plot to any point along the curve represents the climb gradient. Based on the characteristic shape of the climb curve, we see that the condition for best climb angle will always be at a lower airspeed than the speed for best rate of climb. So in a tight runway environment, the pilot will fly the airspeed for best climb angle as soon as leaving the ground, at least until the obstacle is cleared. From that point onward, the pilot flies the airspeed for the best rate of climb in order to minimize the time to climb to cruise altitude. Now, all of these key performance metrics that we've been discussing are not just for setting world records. Airspeed for best climb angle, airspeed for best rate of climb, service ceiling, absolute ceiling, time to climb, stall speed, maximum speed, and speed for optimal cruise appear over many pages in the operating handbook for any aircraft. Before ever taking off, good pilots carefully review the performance specifications for their aircraft, both in order to safely and efficiently fly the airplane at all, and to determine the time and fuel needed for any particular flight. Understanding the performance envelope is important for any pilot.